Well, welcome to I²CNER webinar. Okay. My name is Takata. I'm a research professor at I²CNER. So today we have a speaker from UK, Professor Daniel Orejon. He is one of the most prominent young heat transfer scientists in UK. Before going into his talk, I briefly introduce his background. So he received a PhD from the University of Edinburgh in 2013. Then, right after finishing PhD, he joined with I²CNER as a postdoctoral research associate. So in 2013 October. So 3 years later, so he was promoted to assistant professor in 2016, and in 2018, he got a position as a lecturer in the University of Edinburgh, the current institution, okay, Institute for Multiscale Thermofluids. And he was promoted to a senior lecturer in last August in 2022. So Professor Daniel Orejon worked for I²CNER for almost 5 years. So he made many research accomplishments, but I think his most significant accomplishment was to find his wife. Okay, so today's his talk is droplets on micro decorated surfaces, wetting and phase change. So Dani-san, will you start your presentation? Thank you.
Sure thing, Takata-sensei. So thank you very much for the kind, nice, and omoshiroi, funny introduction. So yeah, given such a very nice introduction, I will just move into the core of this presentation. And yeah, first of all, just to thank everybody involved with the organization of this seminar, Gina-san, I²CNER admins, and also, of course, Takata-sensei for acting as chair and for keeping him working until 5 o'clock or more today. So why drops? So as you guys know, drops are everywhere in nature. When we wake up in the morning, we have drops in the grass, on our window glass. There are also drops in our glass beer when we ask for some beer, and there is some condensation that start to develop because the beer is cold and the wall of the glass actually achieves the saturation at the due temperature, and water condenses on the wall. There are drops also in distillation, drops and phase change in distillation of whiskey, for example. Since I'm in Scotland now, I always need to put this example. But about all, my favorite place to observe drops and liquid to vapor, vapor to liquid phase change, and I'm sure it's also Takata-sensei's favorite place. It was actually the onsens in Japan, which I really miss. I haven't had the chance to visit Japan since December 2019, so almost since all the pandemic started. So how can drops contribute, and how drops and of course phase change, both evaporation and condensation, how can we actually, why they are important to our daily life and to industry, for example. So I like to put this example. This is the energy flow of Japan. I think it's available from the Lawrence Livermore National Laboratory. And here you can see on the left-hand side, this is the energy input in the Japanese grid, including solar, nuclear, coal, etc. But what I like to do is look at the right-hand side here, where we actually have from the energy that we are putting into the system, how much energy is actually utilized versus the energy rejected. And when we do a little bit of analysis here, we can actually see that from electricity generation, there is around 56% of the energy that we put inside is wasted as heat or other energy source. From industrial waste, from industrial use goes all the way to 50%, and from the transport sector is the highest, around 80%. So if we look at this number, around 57% of the energy wasted in the Japanese is wasted from all the input. And because I am now in UK, I also need to look what are the trends within UK. And although you can see that the energy in UK is almost half that of the UK, that of Japan, we are also 3 times less population than in Japan. But you can see how the numbers are pretty similar: 58%, 48, and 78 for a total of 53% of energy waste. And it's here where the phase change, heat transfer can play a significant role. And just by being able to decrease even 1% this energy waste, there will be very big savings in CO2 emissions. That at the end of the day is our mission and the mission, of course, of I²CNER. So some of the applications where we could implement drops, phase change, evaporation, condensation to try to improve the system is, for example, for the management of IT data servers. Currently, the air conditioning units and refrigeration systems account for 1 or 2% of the total energy consumption in the world. So they could be improved and we could have bigger savings. In the case of cars, for example, for cooling of engines, if we were to implement phase change instead of single phase, we will be able to decrease requirements for the cooling system for the engine, reducing the weight of the car, run more miles with the same fuel. In coal-fired power plants, for example, there is this study here from Biretol that reported that if we are able to halve the working pressure of the condenser, moving from 0.065 to 0.003 megapascals, we will be able to increase the overall efficiency of the power plant up to 1.5%. Again, doesn't seem much, but taking into account that most of the energy, at least 50–60% of the energy in the world comes from coal-fired power plants, this will be also huge increases in efficiency and reduction of CO2. And another application is also for water harvesting. For example, there are many regions that are arid and they don't have access to drinkable water. But as we know, in the environment, we can find such a water that is in the moisture of the ambient that could, to some extent, be captured for our purpose. And all these kind of applications and my research as well, I like to link it with the United Nations Sustainability Development Goals, more in particular with number 6, clean water and sanitation, and number 7, affordable clean energy. So once I have introduced a little bit of the motivation, I wanted to give you a little bit of background. I don't want to pay much emphasis here. This is a very nice figure that Wan San, as assistant professor at I²CNER, created for this review paper. And it just exemplified that although a drop, it looks like a very simple system when we just see a drop on our desk, or a drop in the window, it looks like it's a very, very simple system. However, as you can see here, there is an interplay between many different phenomena taking place, both heat transfer, phase change, there is wetting effects, spreading effects, different internal flows within the droplets that make this system more complex, and with, at the end of the day, with also many capabilities that we can actually implement for our advantage. So here is an example of a droplet evaporating, and we can see here that yeah, we may have mass diffusion, we can have convection inside of the droplet, the heat transfer towards the substrate, wettability also plays an important role, and all this, as the droplet evaporates, can actually be utilized to create nice and confined patterns in the droplet. But it also helps us, all these patterns, for example, it also helps us to understand how the droplet evaporate and what are the final conditions upon the complete phase change. And here on the left, we have the opposite phenomena, because during my PhD, I was actually involved in all the study regarding evaporation of droplets. However, when I moved to I²CNER, because of the capabilities of Takata Sensei's laboratory and because of his encouragement to dive into a different topic, I actually started to look into the opposite phenomena, that of condensation. That, as a simple side, it looks also that there will be many similar phenomena taking place, but also you can see that in occasions mass diffusion, convection, heat conduction actually differs. And depending on the wettability, for example, of the surface, you can have also different condensation mechanisms and different droplets or a different shape of the droplets that at the end of the day, they are going to influence our heat transfer during phase change. So now that I have done this small introduction, I'm going to have here all the 4 different topics that I would like to introduce today. Maybe for the last one, we will not have much time, depending on how detailed I'm on the other ones. But basically, I wanted to introduce here different fabrication techniques that I have explored in the past years. So one of them is deep reactor ion etching. All this technique, pillars fabrication, has been done at the Scottish Microelectronics Centre. So this is kind of new research for me since I joined the University of Edinburgh. I wanted to introduce a soft lithography as well, and how we can replicate the features of plants using this technique. This work was done while I was an assistant professor at I²CNER. And so in both of these processes, we can actually get sort of control structures. In the left one, deep reactive etching with very accurate resolution, and we are the ones that we decide what are the patterns. In the case of the soft lithography, very good microscopic resolution, a little bit less than nanoscopic one. But in this one, we can replicate, so we can actually copy the structures either from other structures or even from plants or living organisms. And then we have chemical etching, another different technique to be able to make structures on our surfaces. Although in this case, because it's just chemical etching, we just put our sample in the solution, we are not able to really control the deterministic nature of these features, and they are typically arranged not randomly, because we can control the size to some extent, but yes, we don't have as much control as with the previous techniques. And another topic that I am trying to combine lately is basically the use of structure surfaces that combine a sort of wettability gradient or thermal gradient with slips or lubricant-infused surfaces, which we know that they have very low addition to a surface and they are quite mobile. So going into the first topic. Wetting on microstructure surfaces. This is one of the projects that I was involved as soon as I joined the University of Edinburgh. And in this project, we use surfaces with varying spacing, but fixed diameter and height. And there were different type of geometries that we created: circular, square, star, and triangle pillars. Then we put these surfaces in our drop shape analyzer, and sometimes within a custom build setups, so that we can actually image from any side that we want, from the top, from the side, do some sort of analysis of the different azimuthal angles, for example. So when we started this work for our student, Veronica, she started with water on different pillar geometries with fixed spacing. And in these geometries, actually what we see is just a drop that balls up and sits on the surface with very high contact angles because the surfaces are hydrophobically coated. So hydrophobic surface with structures, high surface tension fluid, the droplet just balls up and does not wet the surface. However, when we move into ethanol, organic solvent also very much used everywhere, and it's necessary to really know what are the different properties and characteristics, how it wets, how it evaporates. So when we did this on these different surfaces that I just show now, you can see that because of the wetting nature of the ethanol, it tries to spread and wick through the structures, and depending on the spacing here, and also depending on the geometrical configuration that we had. So we had circular pillars here, square pillars here, sort of a start here, and triangle. So also we can see, so if the spacing is large, because the length scale of the spacing is also larger than that of the microstructures, the droplets typically, they look very round because they barely see the structures that are underneath. They behave almost like in the smooth surface. However, when we decrease the pillar spacing, because we are having many more structures, and the ethanol tries to wet all these structures, then the droplets start to acquire different types of shapes. So for regular type of structures, we typically go from a square, octagonal, circle. However, when the structure is not completely symmetric, as in these three cases on the left, we have a triangle. Actually, it favors spreading in some certain direction. So by favoring this spreading in some certain direction, the droplet elongates. And what Veronica further did here, it was to put nanoparticles on these ethanol droplets and observe how the different ethanol concentration that we have here affects the different patterns. So we can see that we have, as we increase the concentration, we have from very faint patterns to more concentrated patterns, here more at the contact line and then at the center. So this work again was done by Veronica, and she got a couple of nice outcomes, publication in the Journal of Bionic Engineering, and we recently also published a chapter within the drying of complex fluid drops. What I just show you now is just a brief small taste of what you will find, of course, in both this publication as well on the book chapter, where we have further provided many more results and more analysis and discussion on the phenomena. So motivated from this, seeing that how the different surface tension of the fluid may affect the wetting behavior, we isolated one type of geometry. In this case, we are looking into circular pillars, as we can see here, and that are varying in the spacing, similar as what you saw before. All this work has been done by my student, Holud, that is funded, self-funded, funded by her government, by the government of Oman. So we had 6 different type of surfaces, 5 micropillar spacing, 10, 20, 40, 80, and 160. And what we did is we varied the concentration of ethanol. So we have ethanol, water mixture here. So 0% means is water, pure water, 100% means is pure ethanol. So from here, we can see that when the spacing is small, when we have water, high surface tension fluid, the droplets round and ball up, and we have high contact angles like the one we saw before. And this is typically called the Cca regime, where the droplet just sits above the structures without wetting. However, as we increase the concentration of ethanol, because the surface tension of the mixture changes, decreases, lower surface tension fluids tend to wet more. They like more the surface and the other way around. Then we can, because of this induced spreading, we are actually moving towards smaller contact angles. The droplets wet more, and we have a different regime here where still is non-wetting, but is not in the Cca, is in the non-wetting Wenzel regime. And then we have this other region here at the bottom in red, where the droplets actually quite spread and typically spread more than the original surface if it were flat. So here is basically the same similar regime map, just based on ethanol concentration and spacing here. And as you can see, here we can actually have different geometries of the droplet depending on the surface tension and the pillar structure. As mentioned earlier, for large micropillar spacing, the droplets basically do not, they almost do not see the surface, and typically when we are here to the right-hand side, doesn't matter the type of fluid, then the droplets behave almost like on the smooth surface, round and with a circular geometry. However, when we decrease the spacing of the pillar, actually the droplets start to see more structures. For high water concentrations, droplets are round, as mentioned earlier. For high ethanol concentrations, the droplets start to acquire some sort of octagonal or even square shapes, as you can see here. So this is the regime map that we found for our ethanol water mixtures. And we did, of course, more analysis that is not shown here to demonstrate with classical wetting equations, the Cca equation, the Wenzel partial wetting and partial non-wetting Wenzel equations, and provided this sort of boundary that limits when a droplet will sit either in the Cca state here, in the partial non-wetting Wenzel, or in the partial wetting Wenzel, and how the different parameters of the height and diameter, so related to the pillars geometry, how they will affect the wetting behavior. But this was not enough, because we are only producing we are only showing one single type of fluid. And of course, this sort of regime map may not apply to other fluids, right? So what we did is I have just flipped this regime map to be able to match the other figures that we had from our experimental observations. And you can see here that for our ethanol water mixture, this is the one we originally proposed. So the regime map shown here is basically in the same kind of same qualitatively than the one we propose. Then we also move into acetone, also an organic fluid, similar surface tension, although it looks like when they are mixed at low acetone concentrations, the surface tension is much lower than in the case of ethanol, but seemingly than the case before, we can also kind of get a similar type of boundary for this for this wetting fluid, while we also did the same for a less wetting fluid. In this case is glycol, and again very similar boundaries than the ones that we saw before. And this was published in the Journal of Colloid and Interface Science, and in all the work was done by my student, Kholoud Al-Balushi, and in collaboration with Professor Kelly Sepia. So after this, because wetting, of course, is important, but we are also interested on phase change. But before that, I'm also going to introduce actually a further study on wetting on these structure surfaces. So the results that I showed you before, they pertain to intrinsically hydrophobic surfaces, whereas if we remove the coating or if we don't apply coating, we have an intrinsically hydrophilic structure surface. And what we decided is try to understand how the different regimes also work when we are in the intrinsic hydrophilic configuration. And as we know, cleaning of the surfaces is very important. We want to do experiments on this type of works with the most kind of ideal conditions. So, of course, we did clean the surface with ethanol, and we did experiments before and after the cleaning with ethanol. And you can see here from this kind of map that when we are introducing ethanol concentrations, so the concentration of ethanol increases, the droplets wet more. There is we also see this kind of shapes. Shapes start to be more irregular, as you can see here, but there is at some point that the fluid, because of the low surface tension, the fluid just wets and spreads all over the surface. As you can see here, when we look at before and after cleaning with ethanol, there is not so much differences, and it's not so interesting. However, when we clean the surfaces with oxygen plasma or air plasma, right after cleaning, this is for water, as you can see here, right after cleaning, you put the droplet and the droplet just immediately spreads all over the surface. So they are very high wetting surfaces right after cleaning. Waiting 3 days, you can see that we start to have like some kind of regular shapes, but all these ones after the contact line, in most cases, we can see some sort of hemi-wicking behavior. So the droplet is not self-confined as before, as after cleaning with ethanol, but it actually keeps spreading. For high pillar structures, you can see that the droplets they don't have a kind of axisymmetric shape, symmetric shape at all. However, when we wait even more, you can see here that now it is possible to actually get a more well-defined droplet footprint, and the droplets start to be also more regular in shape. So with this, I wanted to point out that in the case of hydrophilic surfaces, when the material is not coated, there is typically some interaction with the environment, and as the time passes, this interaction is greater, and the surface becomes more hydrophobic. This is why at the beginning we could not deposit, we couldn't see a drop upon deposition, whereas as we move forward, we in time we are able to see these droplets showing a nice shape. And just at the bottom, there are some of the people that are currently contributing to this work, and I will try to present more details, more specific details on this work on the next APS DFD, so the American Physical Society Division of Fluid Dynamics meeting this November in Indianapolis. So once I have talked a little bit about wetting, I wanted to include also our efforts on phase change, also on structured surfaces. Let me remind you, for this evaporation study, we use hydrophobic coated micropillar surfaces. So the same surfaces that we saw the wetting characteristics before, where when we have short spacing between pillars and high surface tension of the fluid, water, we get nice and round droplets. Whereas when we move into and short spacing, whereas if we move into larger spacing, the droplet starts to behave more like on the flat, smooth surface. And as we decrease the concentration, we also decrease the contact angle. Okay, so the very same surfaces introduced before. And here on the left-hand side, I have a summary of the 4 main type of evaporation mechanisms that take place on structured surfaces. So one of them is the Ccr mode, or constant contact radius mode, because the contact line is typically pinned and evaporation takes place with the same contact radius over the period. And what it decreases to account for evaporation is basically the contact angle, as you can see represented here in red. Another evaporation mode is the Cca mode, or constant contact angle mode. In this case, is when the contact line is actually free to move. Is not very, doesn't occur much in the structured surfaces, because the small structured surfaces induce the pinning of the droplet, hence this Ccr mode. So in the Cca mode, what is happening is that the contact line is free to move, and the contact line recedes, while the angle of the droplet is kept more or less constant during most of the evaporation. We have the mixed mode, where both contact angle and radius decrease in time. This is typically observed at the very end of the evaporation. And we also have a stick slip mode, where, because of these small structures, the droplets evaporate, and once it has evaporated a certain amount and the droplet has gained certain free energy because of the evaporation, then the droplet is able to jump to the next pillar, or is able to the pin. And as a consequence, we have this stepwise fashion where the contact angle is pinned, then jumps, pin, jumps, while the contact angle for each of the jumps, contact angle increases to account for evaporation. So those were the four main regimes. Now I'm introducing here the experiments on high surface tension water and 20% ethanol water on 3 different pillar configurations. Remember, very close spacing versus large spacing, almost smooth surface. So when we look into these evaporation regimes, you can see here we have a solid line that represents the average, whereas the kind of shaded line represents the standard deviation of at least 3 experiments. So you can see here how hard my PhD student has worked. I think overall he has done more than hundreds of experiments on evaporation to try to understand better how pure fluids and binary mixture behaves on these surfaces. But mainly when we look at the surfaces, what we can see here is that mainly we have droplets initially evaporating the CCR, as mentioned earlier, contact line pin, and then it typically, because of the structures, it typically goes into a stick-slip behavior. So we have contact line kind of pinning, jumping during the evaporation. But interestingly, because of the nice resolution of our measurements, we were able to also, and our technique, we were able to focus really well in this area here at the very end of the evaporation, and we were able to report a different mechanism than the typical stick-slip. Remember the stick-slip behavior I just showed you before. Typically, the contact angle typically ranges always within the same values when this stick-slip is happening. So is the case of this yellow area, where you can see here stick-slip behavior of the contact angle, as well as here all the values remain oscillating within the same values. However, at the very end, where we are meant to have the typical mix mode, because of the presence of the structures, what we see is actually a sort of decreasing contact angle mixed stick-slip mode. So we don't have the stick-slip oscillating in the same rate. We actually have stick-slip decreasing, and understanding this is very important to be able to kind of pinpoint what is the last moments, what is the surface energy, what is the shape, what is the behavior at the very last moments of the evaporation. That in the case of droplets where we have some particles dissolved, this will play a major role on how the deposits arrange. So it's very important to understand this. When we move into higher ethanol concentrations, remember the droplets wet more the structures. We are starting with lower contact angles, but as in earlier cases, we start mainly with the CCR constant radius mode because of the pinning. But it's very interesting in this, actually for 20 and 60%, what we saw is that there is a region here where you can see how typically the contact angle either stays constant or decreases because of evaporation, right? But as I am drawing here now on the surface, you can see that in all these cases, there is actually a regime, a time where the contact angle is actually not decreasing, is actually increasing. So we are having this other behavior also in a mixed stick-slip fashion. So this behavior also not reported before, and also important because this increasing contact angle also affects the radius. If there is conservation of volume, increasing contact angle means that the radius is going to decrease faster. So the footprint of the droplet is also going to decrease faster, as pointed out here. This mechanism here above, as you can see here, this is just a consequence of the evaporation and the presence of structures that induces more pinning, and it doesn't allow the contact line to recede quick enough for the contact angle to keep constant. However, in this other case, down here, probably Kita-san and Takata-sensei will know the reasons for this, because in the past we worked with ethanol and water. We actually worked with ethanol, but as we were evaporating ethanol in the conditions that we were investigating with high relative humidity, the ethanol was actually transitioning into water. As that happened, the surface tension of the fluid changes, then it increases because water has higher surface tension as ethanol. And what was happening is that our contact angle was increasing in time as the droplet evaporated all the way to the contact angle of water. Here is not exactly, well, it happens also for our case with, we have 100% ethanol, but the main reason here why we are having this mixed stick slip with an increasing contact angle is basically that we have ethanol, water binary mixture. Ethanol is more volatile than water. As ethanol evaporates, the surface tension of the droplet also changes. So as ethanol evaporates, the droplet, it behaves more like water-like, and as such, it wants to be more round. It wants to be more spherical. As you can see here, the contact angles, as reported earlier, increase. So two new sort of mechanisms complementary to the stick slip, where our contact angle increases and decreases depending on the conditions studied. So my student also, in order to try to give more insights on how droplets evaporate on microstructures, she analyzed the different times, normalized times, at which the different droplets, the different ethanol concentrations, and the different pillar spacing, so how the normalized time of the different regimes behave. So as we can see here, we are able to draw this sort of boundary, where for small spacings and for water, so high surface tension fluid, we actually get pinning of the contact line for longer. So the initial, typically the initial stage takes longer for the contact line to sort of depin and move into a different droplet footprint than when we look at the different ethanol or binary mixtures. Stick slip, regarding the stick slip behavior, so it looks like also there is a big boundary here. So all droplets, most of the droplets actually on structure surfaces will display this sort of stick slip behavior. Note that both here, this is the stick slip traditional one that we have, that it has been reported in the literature with the constant contact angle range varying, whereas here we also have the mixed stick slip where the contact angle either increases or the contact angle either decreases. And for this mixed slip mode, as mentioned earlier, we need ethanol in most cases, about all for the increasing contact angle mode. We need some ethanol present in the mixture. These two figures here at the bottom, they just tell us from the mixed stick behavior, it just tells us how much it works, how much the behavior is in the decreasing contact angle mode or in the increasing contact angle mode. And as pointed out earlier, for the contact line to sort of be for the contact angle to be able to increase as the droplet evaporates, there is need for having ethanol on the surface. So next, as you can see here, the behavior is very, very complex. There is so many parameters that we can look at to try to give some nice further explanations on the different wetting behaviors as well as phase change. And these figures here, what they give us is a little bit of a summary on the jumps of the contact line as they evaporate. And I think from here, the takeaway points, the main takeaway points are basically that when we are having short spacing, the droplets, all this stick slip behavior are governed basically by the structure. So most of the jumps that are taking place during the evaporation are in the same order of magnitude as the pillar spacing. This is true for 5 micrometers, 10 micrometers, 20 micrometers as well, where you can see here that the average values are always in the similar range as the pillar spacing. However, when we move into larger spacing, we can see here that these jumps of the contact line, the average jumps of the contact line, now in most cases, they lie below the pillar spacing of the different droplets. Same here. So this is because as the droplet, as the pillar spacing gets larger, the droplet behaves more like on the smooth surface, and every pinning of the contact line, the pinning force is not enough to, as it evaporates, is not enough to later on ensure the jump of the contact line towards the next pillar structure, as we can see from this figure here. So always the jumps are below the pillar spacing. And to notice also from this figure, to notice that as we increase our ethanol concentrations, so you can see here for 60 or above ethanol concentrations, you can see here that the deviation on the measurements, so standard deviation, maximum and minimum values also start to get bigger. This is because the different for higher ethanol concentrations, and as I mentioned earlier, we are getting more irregular shapes, so square, octagonal, and those irregular shapes do play a major role on the pinning behavior and on the pinning behavior of the contact line. So this work was done mainly by my student, Holut, and in collaboration also with Professor Sefian. And I was very glad to for her that she received the best poster for experimental research at the UK Heat Transfer Conference. So I think, yeah, I'm gonna do a summary of this, and I think I'm gonna skip to the very last part of the presentation, although I had like a couple of more topics to talk about, but for the convenience of time, I think I should sort of end up the presentation here. So yeah, as I saw earlier, the first part of the talk was to provide a unified wetting regime map that couples surface tension and solid fraction, so that the day of tomorrow, if we want to have certain droplets with certain shapes on the surface, we are able to utilize the size and the surface tension of the fluid that we want.
There will be a file on page 29. Thank you.
Effect of ambient exposure. We show how the different wetting regimes change in time. And we also provide some guidelines on how droplets evaporate on binary mixture, and we provide 2 new stick-slip behavior regimes. And the findings can be found here. I'm going to apologize in advance. We will have a fire drill, just the announcement in 5 minutes. So I will try to mute myself during that period, but yeah, we can continue with the presentation or with the different Q&A. So before I finish, just a couple of more minutes. I just wanted to introduce very quickly in this slide that yeah, we are not just doing all the research that I just presented, looking at the wettability and the different surface tension of fluids, but we are also very much interested on how the atmosphere actually interact with the surface and how the wettability changes in time, as one of the parts that I saw before. And I am very happy to be able to keep working in this topic with some of my collaborators that I acquired while I was at I²CNER, for example, Professor Takata, as well as Professor Milkovic from UIUC, and other of his colleagues that some of them might be also in this presentation. I secured a small grant from the Royal Society, and I was able to buy this very nice microgoniometer that I had the pleasure to use at the University of Illinois when I was in a placement there, to be able to study the advancing and receding dynamics. And I have a PhD student, Janice, that she has just started last week. And then I'm also very much interested on functional surfaces for condensation phase change. And to this end, I have a PhD student, and I'm working on this topic. Here, very briefly, there are some of the capabilities from my lab in case you like any of the topics or research that I introduced before, and you would like to explore any of these techniques. And just to finish, I would like to introduce that we are organizing the International Conference for Boiling and Condensation Heat Transfer that takes place this May in Edinburgh. And we have already secured very nice, not prominent, very well established researchers in the topic. One of them is Professor Takata, here acting as chair today. I hope to be the chair of his session to pay back. And we also have Professor Nena Milkovic, who will be keynote presenters at this conference. As a bonus, to say that Edinburgh University has been selected by Times Out as the 10th best, as well, not the 10th, as the first best city in the world, even over Chicago. So this topic is interested to many of the research that is carried out at I²CNER within our trust. Research carried out by Takata Sensei, Milkovic Sensei, etc. But we are additionally organizing and having this September, 3rd to 6th of September, the Heat Power Cycles Conference that is also very much related to the goals of I²CNER for the creating more efficient heat transfer and heat power cycles. And here are some of the invited speakers, very interdisciplinary, from CO2 absorption to heat transfer, etc. And again, Edinburgh as top city in the world. And I just put this slide here to acknowledge some of the people that I was going to present some of the research, but I ran out of time. and my current laboratory members, as well as
please leave the building by the nearest available exit. Do not use the lifts. Exit. Do not use the lifts.
All right, I think the announcement is finished. So yes, I just wanted to point out that I just wanted to mention and thank all the partners, all the sponsors, as well as all the collaborators. Yes, thank you all. Thank you.
Thank you very much,
Sorry.
Danny-san.
Sorry about the alarm. Probably I woke everybody up, right?
Is it a fire drill, right?
Yes. Also to tell me that I had to finish.
Okay. Yes. Thank you very much for a very interesting, excellent talk. On the droplet, behavior.
Thank you, Sensei.
Substrated surface, and also thank you for introducing the boiling conference. Okay. Okay. So we still have some minutes for question and comment. And
of course.
Wan-san,
Please.
Wan-san, will you ask a question? Moment.
Question disappeared.
Disappeared? Sorry.
I can see it here. So we cannot let them ask the question. I can read though. So thank you very much, Danny-san. Thank you, Wan-san, for attending the talk and for your nice comments. So your question is about the slide 9. I think, am I sharing the screen, Sensei?
Yeah.
Yeah, so yes, this is
slide
okay.
9.
So slide 9. So your concern is about the evaporation of alcohol very fast and how long it takes the measurement, and to avoid evaporation effect and get systematic results. So completely agreed with you, Wan-san. Is very important. As we know, ethanol evaporates very, very, very quick. And even it can evaporate a little bit when we are dosing the droplet. So when we are creating dependent drop before deposition, we are already starting to have ethanol, preferential ethanol evaporation. So here I think my student, she tried to minimize this, and the only way without implementing very complicated control measurements, I guess, is to ensure the measurements to be done as fast as possible. So to this end, I think, yeah, she was dosing and depositing the drop within the first few seconds, as well as acquiring the contact angle for the just right after deposition. And this was carried out several times. So she repeated experiments 2 to 3 times. So yeah, you can see that for water, actually there is not much of an issue. And for water, independently of the spacing, the deviation is very small, right? Because we are having pure water. Also for high water concentrations, the same. But when we move into more pure ethanol, and above all in short spacing, where the structures have more impact on the wetting and the final shape of the droplet, you can see how the standard deviation actually increases. This is also related to the more asymmetric size of the droplets, as well as later on with the preferential evaporation, as you mentioned. So yeah, ideally, I think this is the kind of best thing to do. There could be maybe a scope to implement a chamber to maybe saturate a little bit with ethanol to not, so that ethanol does not evaporate, but probably that ethanol in the environment will also condense in the water droplet later on, and it will actually kind of mess up a little bit the results. So yeah, this was our approach, both for these results as well as for the acetone. In the case of glycerol volatility is not as high as that of ethanol. So in the case of glycerol, this was not such a big issue. I hope I answered your question, Wansan.
Okay, thank you. So we have two more questions on the message.
Excellent.
First one is from Yutak. Okay, so great talk, Dani-san. On the first topic, how was the drop deposited on the surface? Would the time with the impact Weber number affect the spreading? That is a question.
That's a very good question, Kita-san. Thank you for that. And I really understand your question, because for this type of surfaces, right, hydrophobic micropillars, to some extent, the droplet can be in a sort of super hydrophobic regime, right? I remember Kita-san has done very beautiful experiments on similar surfaces where he used to put the droplet actually at the boundary between two different surface tension, two different geometries. And he used to see the droplet, how it moves. And as he knows, is sometimes if the surface is very hydrophobic or super hydrophobic, it's very difficult to deposit the droplet. In this case, because the large surface tension, surface area in the case of short spacing, and because of the sort of wetting behavior when we increase the spacing, these droplets actually, we used to put the syringe, we dose the droplet on the syringe, and after the droplet is brought into contact with the substrate, either by bringing the droplet down or by bringing the substrate up and then separating them. And these surfaces, again, because of, you can see here, the contact angles are not as high as on a super hydrophobic surface. So there was no need for us to drop the droplet from the needle as in other type of experiments or in more super hydrophobic surfaces where it's kind of needed. So basically just moving the droplet or the surface in contact with each other very gently until they touch, and then detach them very gently.
Okay, the next question is from Nguyen-san. Thank you so much for the wonderful presentation. I am very new to this field, so I want to ask a very naive question. In the wetting DRIE coated microstructure surface, why is a difference between symmetrical round drop and asymmetrical drop important? That is a question.
Thank you very much, Steve, for your comment and also for the question here. So yeah, maybe I didn't put much emphasis before. Maybe some schematics will have actually helped even more to explain this sort of asymmetry of the droplets, right? So just as a sort of reminder, as I mentioned earlier, when the spacing is large, this means that we have structures very far away from each other. So when the spacing is large, the droplets, the pillar, actually the characteristic length of the pillar is much smaller than that of the spacing. Then the droplets, when we put them on the surface, they barely feel the structures. And this is why these droplets, they typically have very round shape. Even in these cases here for ethanol, they have very round shape, and their contact angles are very similar to those on the flat surface here. So for short, large spacing, just think like there are very few structures. The droplets just behave like on the smooth surface, and they present a circular footprint. When we decrease the spacing starts to play a major role on the droplet shape. Okay, in the hydrophobic ones that we are presenting here, when we have high ethanol, high water concentration, pure water, and high water concentrations, the droplets have high surface tension, and they tend, for high surface tension, they tend to round up when they encounter a hydrophobic or a super hydrophobic surface. So this is why here, 40% ethanol concentration or below, we typically have also very nice round droplets, but in this case, they sit above the structures in the sort of Casey-Baxter state, okay? And it's basically this quarter here, right, the top left, when we start to see these major differences in the droplet asymmetry, and we start seeing octagonal and square surfaces. And here is basically because of the lower surface tension of the fluid. Ethanol, in this case, lowers the overall surface tension and tries to weak through the different structures. And it is both the combination of surface tension, the intrinsic hydrophobicity of the surface, as well as the different spacing between pillars, what is gonna govern these geometries, what is gonna govern how the fluid dust spreads in either of the directions, and the final kind of footprint of the droplet. And typically when we have symmetric patterns of the pillars, we can see again that the geometries of the droplets are also symmetrical, whereas when we have non-symmetrical pillars, in this case they are a triangle, the droplets sort of elongate in the shape of, in the direction of the triangle. So again, here also different geometries. And again, it's because of the interplay between a wetting liquid, the pillar structures, and the pillar spacing, how the fluid is going to spread or weak within the structures, giving this final geometry. See, I hope I answered your question.
Yeah, thank you very much. And Kubota Sensei has a question. Kubota Sensei.
Of course, Sensei, please.
Thank you very much. So, thank you for nice presentation. But I'm not familiar with this topic, so sorry, I couldn't catch. So why the droplet showed that wetting behavior? Okay, so you showed many examples of the wetting shapes, but if the conditions are changed, the wetting behavior is also changed every time. Okay, so you need endless experiment. So my question is, what is the salient factor that determines wetting behavior?
What is the, sorry?
Salient factor, governing factor.
Governing factor.
The governing factor.
What determines the wetting behavior? If you don't understand the governing factors, so you cannot make modeling.
The model, right? So definitely on surface wettability. So the termination, the outermost layer of the surface is what is going to tell you if a fluid is going to wet the surface or not, right? Most, I will say, all known materials, metals, for example, they are hydrophilic. They like water, right? So when we put a drop, we know that the droplet is gonna spread on the surface independently if it has structures or not. Then the structures, what they are gonna do is they are gonna enhance that spreading or that wetting behavior. And on the other hand, if we apply a coating to make them on the other side, to make them hydrophobic so that they do not like water, the structures are actually gonna act and are gonna enhance the opposite behavior of non-wetting. So definitely the most important one is the wettability of the surface. And then what we have found is that, yeah, in occasions, you actually don't need a coating to make your surfaces hydrophobic. This is what I saw here. And this is also in some work with Professor Milkovic. You don't need the surface to have a coating. Sometimes just with exposure to the ambient, you can make the surface a little bit more hydrophobic. So yeah, if you ask me for what is the main mechanism, what is the main thing governing all this shape of the droplets, definitely wettability.
Wettability. All right. Okay. So in the future,
it's a very difficult question. Yeah, basically.
Yeah, I know.
Maybe you can come to my office and we can discuss, or I will explain with using sake or beer.
Okay, good.
Droplet.
Very good. Thank you.
And okay. coffee as well, right, Sensei?
Dani-san, one more question. One more question from unknown name, but
anonymous. Yeah.
Thanks a lot, Dani-san. It was great listening to you. Apart from the DRE MRT jot, can you briefly speak about soft lithography method? Soft lithography.
All right. So yeah, thank you very much for this question. So yeah, I had it in my presentation. No, normally we try to have like one slide per minute when we do a presentation, right? More or less, but I think I spent all my 45 minutes just with the first 18 slides. So I was not able to introduce any of this research on soft lithography. So basically this soft lithography was done when I was assistant professor at I²CNER. And we had this PhD student, Vipul, that he's actually now a postdoc at Finland University. And he was very much interested on bio-inspired materials. And what he did is basically he identified from many different type of leaves. He identified the dragon's lily or Gladiolus daleni as a potential candidate for exploding and for water harvesting. And then what he did, he got some leaves that, as you can see here, from SEM images done at Kyushu University. You can see here how the microstructure arrangement, the microstructures and nanostructures are present in a very well arranged manner. So what this soft lithography replication consists of is basically to have the sample that you want to replicate. Then you apply a polyvinyl sort of silicone that is initially in kind of liquid phase, and you put it on the Gladiolus danelli, applying a little bit of pressure so that this polyvinyl siloxane kind of fills the different spacing between the nano and the microstructures. And you leave it here, as say here, cure for 15 minutes so that it hardens. Once it hardens, you can actually peel it. And you get the so-called negative replica. And then what you need to combine is this negative replica with the epoxy unhardener, also in a sort of not liquid, but kind of malleable state that upon you put your PBS that is solid, it's gonna mold and it's gonna give the positive replica. So trying to replicate again the structures of the original surface. So for this process, 3 hours curing, and then again you just peel the PBS as we did before. We remove it and we get the replica on this sort of material epoxy that is actually hydrophobic. And we did an SEM also on these structures, and you can see here that also, so at the micro scale, the arrangements, the spacing between the structures is kind of kept. We also have lines of these small microstructures here, and also the size, diameter of these microstructures were quite replicated. I don't know if you guys can see also, but it was also able to replicate trenches inside of the leaf. So yeah, the PBS was able to kind of go inside, and then we were able to get it here. So at the micro scale, very good, very accurate replication. When we were looking at the nanoscale though, you can see that for nanoscale features, it fails a little bit more. So a different technique will be better to replicate the nanostructures. And here you can also see, scanning optical microscopy that also proves that the size, spacing of the microstructures, as well as the depth of these trenches were replicated in a very good way. And then we took them and we investigated the mechanisms of condensation, wettability, as well as fog harvesting for these specific surfaces. And just in case you can get more details on this paper published also with Takata Sensei and with Venkata and Harish, who was a previous I²CNER member as well. So I hope this gives you enough details on this specific topic. Thank you.
Kari-san, we have one more question. Maybe this,
All right.
this will be the final one. So,
Perfect.
Ikawa-san, is all surfaces or microstructured surface under drop wetted, or is my micro valley occupied by air? If occupied
Perfect.
by air, how about the effect of ambient pressure? That is
Very nice and good question. Yeah, I think for my next presentation, if really not especially in the topic, I think I need to create some nice schematics and figures, right, Sensei? I think, yeah, for me, this is kind of well understood, but yeah, I understand that for I²CNER, not being all of you guys in this topic, it becomes a little bit more complicated. So regarding your question, a specific question about wetting, you can see here, we identified there are like three differentiated regions here, right? The Cca in yellow, the partial non-wetting in blue, and the partial wetting in red here. So all the droplets that are in this yellow region, these droplets are, as you mentioned in the question, these droplets are sitting above the structures, and there is air trapped in between. This is why we are able to get such a high contact angles. And these were confirmed both by visualization from the side, as well as for the classical Cca equation, that when we plot our experimental results, it aligns very well with this Cca equation. Then, as we increase the spacing of the pillars, or as we increase the ethanol concentration, the droplets, the air between the pillars is now displaced by the water, so or the mixture. So for all this blue region, the droplets are wetting those spaces, and they sit in the so-called partial non-wetting Wenzel. And when we have higher ethanol concentration, because the fluid is more wetting, and when we have more spacing, the droplets definitely wet those structures, and actually the structures induce further spreading of the droplet when you compare to the flat, smooth sample. So in this case, also the droplets, the water wets the surface. Now, when we look closely into the Cca, I think your question and your point is very important, and ambient pressure may play a role. All these experiments were carried out at ambient laboratory conditions, and just for the wetting, we normally see just Cca, and we haven't studied different ambient pressures. In the case of evaporation, though, I have to point out that, yes, droplets initially start in the Cca state, but as they evaporate, the curvature of the droplet changes. And as this curvature of the droplet changes, typically increases the pressure inside of the droplet, and this may cause that the droplets actually just sunk. So droplets that were in the Cca state originally as equilibrium, as they evaporate, they will move and they will sink on the pillars, wetting all the structure. So the droplet pressure is very important, and also, of course, the ambient pressure, it might also affect this Cca. For example, I remember we have a publication with Takata-sensei where in the case of the Leidenfrost, right, we were able to decrease the Leidenfrost temperature by decreasing the pressure of the system. So at some point for this Cca state, if we decrease the pressure, this Cca state will be enhanced. Whereas if we increase the pressure of the system, we might arrive to a point where we don't have this Cca and the droplets will actually sink into the structures.
Okay, thank you very much.
I hope it was clear.
More questions, but because of the time, goes by very fast. And Danny-san, you have to be evacuated from your building because the fire alarm and you will get wet. Okay. Okay, so I'd like to close this excellent webinar. Thank you for your talk, Danny-san, and thank you for the audience participating in this webinar. Okay, so
definitely thank you very much. Thank you all, and Takata-sensei, I'm looking forward to having you in May here. Yeah.
Thank you very much.
Hopefully, some of you I²CNER guys, you can also come to either one of these conferences or just to visit our beautiful city. And I hope I can go to I²CNER also at some point. I really miss Japan. I miss Takata-sensei and many of the colleagues that I met during my time there.
Okay, thank you.
Thank you. Bye all.
See you. Bye bye.